Welcome to this lab. Today we are going to look at using the Jupyter Notebook and do a little bit of the data science to find out is the rise of smartphone usage in the US caused the increase in the car accident. So here is a description. This is a causal inference project. This notebook contains the EDA for the project. The causal inference analysis was performed with R package and available in a RMD file. So the goals and introduction. Driving around this day, it feels like there are more car crashes and more crash-related traffic than there used to be. It also feels like everyone is distracted all the time. Peering into other cars during traffic jams will almost always reveal the other driver using their smartphone. It is well known that distracted driving is dangerous, but most people still have their phones nearby when they are driving and will at least glance at them while they are stopped at red lights or in stop-and-go traffic. Together, these observations lead to question: has smartphone usage caused a measurable increase in the number of traffic accidents in the US? This is a question that cannot be answered through experimentation, as it would be likely unethical to ask a group of people to use their phone when driving. However, causal inference methods may allow observational data to be used to determine whether smartphone caused an increase in the number of car accidents. So, we are going to run the Python script here so that we will see the result. So the library used here is shown here, which is Panda, Seaborn, Matplotlib, Pilot, NumPy, and the datetime. So to understand what each of them is doing, I will ask Copilot to explain. Okay, so from here you can pause the video and take a look at what all these libraries is doing. Okay, so I can just run this and they will import all the libraries that is required for this exercise. As soon as you see the number is this is already finished. Now going to the next one. So we're going to load the data from the CSV, which is already inside my folder called crash by month and also PW cell phone usage. Let's run it. And that is also done. So using the Panda to load the data into the variable crash data and the phone data. So the next one is we're going to do the data structure and characteristic, and that is also done. So the crash data, we will read the top 5 rows of the crash data to get the feel for the structure of the data frame. Next is crash data info. So it's to find out the size of the crash data frame, types of data, and whether they are missing data. So the crash data consists of 15 columns, 45 rows, and is a mix of long white data frame. Year type of crash populations are in the long format, while the number of crashes per month is in the white format with 1 column for each month. Luckily, there are no missing data to contend with. To get this data frame ready for plotting and analysis, it will need to be converted to a fully long format. In addition, the dates, month, year will need to be formatted. The total number of crashes for each month, year will need to be computed. Sum is the number of each crashes, fatal, injury causing, and property damaging, and the total number of crashes per month per year will need to be normalized to the total populations that year. So using the phone data, we will read the top 5 rows of the cell phone to get a feel for the structure of the data frame. Okay, so do the same. We want to find out the size of the cell phone data frame, types of data, and whether they are missing data. So the cell phone data consists of 3 columns and 64 rows. The date column will need to be converted to the date data type. At the moment it's object. The cell phone and smartphone column are both percent and of the adult American population and do not need to be adjusted. There are quite a few missing data points in the smartphone column. So now we will move on to the next one, the data formatting. So the crash data require a fair bit of formatting. The tasks include pivot from a wide data frame to a long data frame, format the date column, sum the different types of crashes for each month, normalize the number of crashes to the populations, add the column designating the season for the year first up, so the data frame will be converted to a fully long format. Let's do it now. So this one is using Panda melt crash data ID variables, year populations, and the type. And then next one is to rename the column variable to the month and change the name. So this is what I'm saying, and then finally read out the top 5 row. Next we will now the crash data is in fully long format, So next, the date column will be formatted. Okay, long crash data month year using this concatenation. Okay, so and the year into one column. And then the date. So we will convert month and year to the date format. Okay, so next one is drop the columns year, month, date in place, clean up the old column. So meaning you remove the, after you have converted all this column to the new column, you will drop it. And now let's print out the data. So you can see the date is converted to date time. Now there is a date column that includes the month and year is in the data type date time 64. Next, the total number of crashes, including all the 3 types, will be computed for each month. Let's run that. Sum the different types of crashes for each site. So using group by. Okay, so there is no longer a type column, and value number of crashes was summed for all 3 types of crashes for each day. Next, the number of crashes will be normalized to population size per 100,000 people. So you're using some crash data population divide by 100,000. And then again, normalize the crash count to per 100,000 people. And then drop the column population value plot in place, clean out the old column. Let's run this. That's done. Finally, another column season will be added based on the month column. By adding this column, it will be possible to test whether more crashes occur in certain season. So we will create a dictionary designating each month to one season. Okay, sum the crash data, creating new column season based on the month. So I added a new seasons in the columns here. It's called, yes, so you will see, okay. So in this year and the date, there is around 169 crashes per 100,000 people, and the season is in the winter. So you see winter has the highest crash. It looks like. Alright, so the formatted crash data frame has 3 columns and 180 rows. The crashes per 100,000 has the total number of car crashes regardless of type for each month of every year from 2006 to 2020 normalized to population. Now we will include the smartphone data usage. The smartphone data require considerably less formatting. The main task here is to format the date column as date time 64. Okay, so let me just run again just in case I forget to run. That is already done. And now let's read the info. So the formatted cell phone data has 3 columns and 64 rows. Additionally, there is still missing data in the smartphone column. So now we will plot the data. Okay, a scatter plot of the normalized crash data over time will reveal any outliers that need to be considered, and will show the general trends in the number of car crashes over time. Okay, using the PLT figure, that is to plot the graph. And then the Seaborn is the SNS, right? Is to do the scatter plot with the x-axis and y-axis, and also the season HUE data, some crash data, and then show the graph. Okay, let's run that. So the plot shows a sharp decline in the number of car crashes in 2020. Clearly, the COVID-19 pandemic, which started in February-March 2020 in the US, had a substantial impact on number of people driving and crashing. The year 2020 is an outlier and will be removed from future analysis. So some crash data. So we are going to filter the date after January 2020, and then do the scatter plot again. So once the outlier year is removed, the overall trend in the crash rate is much more apparent. The number of crashes per 100,000 people appears to decrease steadily from 2006 until about 2011, when the trend reversed direction and the number of crashes per 100,000 starts steadily increasing. There also seems to be a seasonal effect, with more crashes happening in the fall and winter than the spring and summer. However, the overall trend of falling crash rate before 2011 and rising crash rate after 2011 appears to hold for all 4 seasons. Now that the data set is fully clean, it can be exported as a CSV that can later be used for causal inference in R. So this is to export into CSV. Now, smartphone data. Although the cell phone dataset has information about total cell phone usage as well as the smartphone usage, the goal of this analysis is focused on determining whether smartphone usage specifically caused an increase in car accident in the US. A scatter plot will show the overall trend in smartphone usage over time. Okay, so I run this, and then using the same PLT, which is a Matplotlib PyPilot. Okay, so the percentage of American adults reported using smartphone increased steadily from 2011, when smartphone usage first started being reported, to about 2017, when the usage continued to increase but at an apparently slower rate. Unfortunately, the data and the plot do not show when exactly the smartphone usage started taking off. The first iPhone was released in 2007 but did not become popular for a few years after its release. The first Android smartphone was released in 2008 and similarly experienced some lag time before it gained popularity. However, 2011, with smartphone usage reaching 1/3 of the population and the recognition that the phenomenon is significantly enough to record by the Pew Research Center, is a significant year. Therefore, 2011 will be used as the cut point in the ensuing causal inference analysis. As this is the key insight from this dataset, it does not need to be exported for further analysis with R. Now we have hypothesis testing now. Okay, so the scatter plot of the crash data reveal a potential trend in the data. It looks like there were more crashes in the fall and winter than in the spring and summer, regardless of year. This is hypothesis that can be tested with one-way ANOVA or analysis of variance. That's the one. So import function for one-way ANOVA. Okay, so next one is subset the crash rate by season. That's done. Now using ANOVA result, using F1 wave function, winter, you put all these variables into the functions, perform one-way analysis of variance on crash rate based on season. Let's run that. And that is a result of statistic here. In this case, the null hypothesis was that the season has no impact on crash rate since the P minus value is so low, which is this one, much lower than the traditional cutoff of 0.05. The null hypothesis is rejected. The relatively high F statistic provides further support for our hypothesis. As a result, it can be concluded that season does impact crash rate. The ANOVA alone cannot indicate which season has different crash rate, but since the ANOVA result was statistically significant, it is appropriate to apply ad hoc tests such as Tukey honestly significant difference (HD test) that can determine which season have statistically significant crash rate from each other. Okay, so the next one is we're going to import the functions for pairwise Tukey HD test. Okay, let's run this. So using the pairwise Tukey HD and then put in all the variables inside here, perform the pairwise Tukey HD test, and then put in the season alpha 0.05. So the p-value cutoff for the statistic significance is defined as 0.05. Okay, so this is the result. Here the null hypothesis is that there is no difference in crash rate between the two seasons being compared based on the result. The null hypothesis can be rejected to fall, spring, fall, summer, spring, winter, summer, winter. To sum up, the crash rate in fall and winter is significantly different than in spring and summer. You can also read the results here, so I actually asked Copilot to help to do the key findings. Here the null hypothesis is that there is so I think this key finding is the same as the summary here. So in conclusions, the analysis show that based on the available data, increasing rates of adult smartphone usage cause a concurrent increase in the number of car accidents in the United States. This is an interesting outcome, while many people likely suspect the relationship exists. The result of this analysis are compelling evidence for a direct causal link between smartphone and car crashes. However, it remains important to remember there are many other variables at play that could not be controlled for in this analysis. The impact of the COVID-19 pandemic on the car crash data is a stark reminder that other variables could be influencing the effects observed. The number of crashes decreased sharply in 2020, but not because people stopped using their smartphone while driving. There were just less people on the roads to cause the accident. The year 2020 was considered an outlier and was removed from the analysis, but there may have been other data points that were similarly affected by exogenous factors. Moreover, it must be considered whether something other than widespread adoption of smartphones occurred in 2011 that could have reversed the declining trend in the car accident rate in the United States. In this context, it is useful to consider the assumption for regression discontinuity analysis. The treatment variable impacts the outcome, but not any of the other variables. The treatment assignment happens only at one cut point value of the forcing variable. Treatment assignment is independent of the potential outcomes within narrow interval around the cut point. Counterfactual outcome can be modeled within the interval around the cut point. So it is difficult to be sure that all four assumptions are met in real and large data sets such as the one used in this analysis. For instance, it is not possible to know for sure whether smartphone usage doesn't also affect the amount of time people spend in cars, which would violate the first assumption. Importantly, the treatment assignment in this case does not occur at one cut point value in this case. While smartphone usage may have reached a critical adoption rate in 2011, some people did use smartphones before 2011, and the number of people using smartphones continued to increase after 2011. As a result, a fuzzy RDA may have been more appropriate. Furthermore, a more complete analysis might have been possible if the cell phone and crash data were not aggregated at such high level by month and by the whole US. If the counts were instead aggregated by week and by state, extreme weather events could have been better accounted for. Average income and population density are other variables that might be related to smartphone usage and car accident rates. In sum, this will be built upon by finding more complete or less aggregated data set and by applying a fuzzy RDA. Nevertheless, the cost resolution causal inference analysis presented here show that with regards to the information available, smartphone cause more car crashes. That's the end for this lab. Thanks for watching.